Hi class, Miss Cornacchione here and Fiat the Cat. This video is on topic C4, electric potential energy changes, electric potential and potential difference. So obviously there are a lot of terms that sound the same. So let's put them beside each other and take a look at how they're different. So we're going to be in this lesson talking about change in electric potential energy. So that's delta EE or work. Electric potential, which is V. Electric potential difference, which is delta V. I do recommend for this chapter, I believe it would be very beneficial for you to create your own just this chapter formula sheet for yourself, and you can color code it and annotate what each variable represents, what's SI units, which quantities can be positive and negative. So make it your own sort of crib sheet to summarize formulas in this chapter. So in this lesson, we're going to be focusing on understanding these concepts, learning new equations, and practicing examples involving these. So recall, if you have two plates with equal and opposite charge, the electric field that is created is uniform. So anywhere inside, there is a constant electric field of epsilon. I think I said this before. I think I might have said E, but anyways, it's a Greek letter, epsilon, with the vector arrow on top of it because it is a vector. And epsilon has a direction from positive to negative, which is the direction that a positive charge would travel along. And anywhere outside these plates would have an electric field of 0. But inside, the electric field is uniform. And in this field, a point charge would experience force that is parallel to the fields. So we know that electric force is calculated by Q times epsilon. And when we have an equation with vectors, remember that the direction of the vectors must exactly match. So the electric field is positive to negative. Therefore, the electric force points that way too, so towards negative. If we take a positive point charge and place it near the positive plate, when we let go, that positive charge is going to travel towards the negative plate. And I mean, I worked very hard on that animation there, but it's technically not ideal because it accelerates. So remember, F equals ma. When there's a net force, that causes acceleration towards the negative plate. So I wish the animation would allow speeding up, but anyways, I think you get the idea. When we placed the charge at the positive plate, we'd have to hold it there and do work to hold it there because it naturally wants to move to the negative. So that might seem trivial right now, but it's important in the work calculations that we're going to come to. So force is in the same direction as epsilon. So recall that there are similarities between electric and gravitational force fields. And for the upcoming slides, I feel like it's useful to visualize the analogous force of gravity scenario. At least I find that this helps me. So if we have visualized the negative plate of the parallel plate scenario, the negative side as the Earth, objects with mass will experience a force, a downwards force towards the center of the Earth. And it's the downwards force is in the same direction as the gravitational field strength vector G, which is down towards the center of the Earth. The gravitational field vector is pointing down, and objects with mass want to fall down and accelerate in this direction. So the force on objects with mass is down because gravitational field strength is down. And if we take a look at this equation, it actually looks very similar to our equation for electric force. Electric force, Q epsilon, gravitational force, mg. So we've already talked about epsilon being very analogous to G and mass being analogous to charge. Okay, so now continuing with the visual of what happens with the force of gravity or the gravitational fields, motion in the gravitational field, for a ball in free fall, the work done by the force of gravity is positive. The work done by the force of gravity is positive because force of gravity is down, displacement is down. So let's take a look. And then since we go from our initial high EG to low EG, our change in potential energy is negative because remember, delta is final minus initial. So if we go from 0 minus whatever mgh we were at before. So work was positive here, potential energy was negative. So they basically have the opposite sign. But for a ball lifted up, so let's lift up something with mass, work is done against the force of gravity, and it's negative. The change in gravitational potential energy is now positive. So when we take something and we lift it up, the displacement is up, but that FG is still down. So the work done by gravity is opposing, it's work done against the force of gravity. And so it's negative work, but it's positive delta EG because we go from initial, which is a low value, to final, which is a high value. So when we do final minus initial, we get a positive. So work done by gravity is positive. FG and D are in the same direction. Stored energy is lost. EG gets smaller, lower to the ground. And then work done by gravity is negative when FG and D are in the opposite direction, so like this scenario. And the stored energy is gained because we put work into lifting up the ball. So we're adding stored energy into this ball. Take away from this analogy is that so far, so work done by the force field is the opposite sign to the change in stored energy. So the delta E stored is equal to negative work. When the work is the work done by the field. So it is also true for the electric potential energy difference. So the sign of the work done by the electric field, we're going to see that it's the opposite sign to the change in potential electrical energy. So now we have the diagram. I'm using these diagrams, even though you have to tilt your head 90 degrees to see the analogy of the negative plate being here, which is kind of like Earth, and objects with charge naturally want to travel towards the negative plate. I'm using the textbook diagrams just so that you can use this PowerPoint to supplement what's in the textbook there, so you can use them both and you don't have to orient differently. So if you're orienting yourself in this diagram, you see epsilon is this direction. So you know here or somewhere here is the negative plate, and here or somewhere here is the positive plate. Positive objects naturally want to go from positive to negative. Let's take this object from A, so closer to the positive, to B, so closer to the negative. The electric force on the charge is parallel to epsilon, so Fe is to the right, epsilon is to the right. If the charge moves from A to B, so to the right, the work done by the electric force on the charge is, work is force times displacement, and we know work is also equal to the opposite sign of change in potential electrical energy. And this diagram, think of the ball is in free fall, so the ball is coming closer to where it wants to naturally go, so it's losing its stored energy. We combine these two equations to be that delta EE is equal to negative force times displacement. And then we also know electric force is equal to QE. So we sub all those in together and we get delta EE equals negative Q epsilon delta D. So we get the change in electrical potential energy or work to move a charge from one point to another is equal to negative the charge size in coulombs times the electric field strength in newtons per coulomb times the displacement. We are going to sub in with the, oh, I think it's coming up. Okay, electric potential energy is the energy stored in an electric field that can do work on the positively charged particle. It is also the energy stored in a system of two charges a distance delta d apart. Recall energy is a scalar value. So the first part of that sentence we address more in this lesson. The second part we address in the next lesson of point charges. So it's a stored energy. Just like gravitational potential energy, it's like when we increase the height of an object away from the surface of the Earth, it's gaining stored energy that could be released if we let go, and it naturally gains kinetic energy. So this is stored energy associated with being in an electric field. Okay, so in other words, the change in electric potential energy depends on the electric field, the charge being moved, and the charge's displacement. The above equation will give a change in the potential energy as the charge moves through the displacement change in position in a region where the electric field is uniform and parallel to the displacement. And we use the sign of Q in this formula. Actually, I should mention, we use a positive or negative sign for Q based on if it's a positive or negative charge. We also use a positive or negative value for delta D, depending on whether we're going closer to where the charge naturally wants to go or away from it. So we think of this point as like H equals 0. So if you're going this way, final minus initial versus, wait, what did I say? This way, final minus initial would be negative versus this way, final minus initial would be positive. Okay, so if an applied force moves a charge from B to A, so that's the opposite direction, against the electric field, so our applied force is to the left, Fe is still to the right with epsilon being to the right. The work done by the applied force is negative because F and D are opposites. But the work done by the field is positive. Oh, I think I've got these slides backwards. Hold on one second. Yeah, so the work done, if we're moving from B to A, then this is the direction of our displacement, and D and F are in opposite direction, so the work done by the field is negative, and that means F and D are opposites, and the change in the electric potential energy is positive because the work done by the field is always the opposite direction as the potential energy change. So think of the ball being lifted up. We're going to gain stored energy. So that's why this is positive. And the work done by gravity would be negative. Okay, so in that same diagram, so if the applied force, so we moved from B to A. Now if we let go, if the applied force is removed, the charge will naturally want to move back from A to B with the electric fields. And the work done by the electric force is positive. So F and D is in the same direction. The change in the electric potential energy is negative. So now this is back to the ball being in free fall. So you lose your stored energy. You lose your stored energy, and the work done by the field is positive. So that's why this is still true. So to summarize, delta EE is positive when the work is done against the electric field, resulting in energy stored in the field. So this is when we're lifting up the ball. The analogy is with gravity, lifting up the ball. For delta EE is negative, work is done by the electric field, positive work, on a particle, on a charged particle moving in the electric field. Stored energy is lost, which typically increases the kinetic energy of the particle. So that's like when we let go, it typically accelerates towards the negative side. So this is like the ball in free fall, and this is we are putting in work to oppose the electric fields, and we're lifting up the ball. So lifting up the ball, ball in free fall. Okay, so let's do an example. We've got a proton which moves from rest in a uniform electric field whose magnitude is 175 newtons per coulomb. Electric field whose magnitude is, so what's that given? That's epsilon. Epsilon is equal to 175 newtons per coulomb, so that's just good to recognize that we already know that. Do we know the charge on one proton? Yes. If we need it, do we know the mass on one proton? Yes. These are things that are in our like constants in the appendix of the textbook. And maybe I was mentioning for this chapter to draw like a formula sheet or a cheat sheet to kind of summarize all of this. Maybe you're going to want to put the common constants like the charge on a proton. Okay, so we've set up that we know epsilon, we know Q if we need it, we know mass if we need it. Calculate the change in electric potential energy, so that's delta EE, if the proton's initial position is 1.45 meters from the origin, and the final position of the proton is 2.95 meters from the origin. So we've got a position, initial and final position, we can get delta D. So delta D epsilon, so let's start writing this out. Oops. So drawing a little diagram, we've got a positive plate side and a negative plate side. I always tend to I try to remember to draw the negative plate on the bottom so that I can think of the analogy of gravity, like the Earth's surface is negative, unless of course I'm working with a negative charge. But we've got a positive proton. We write out our givens. To find delta EE, we can use this negative QED equation. And then we sub in, so we would look up that the charge on a proton is 1.6 times 10 to the minus 19 coulombs. That's the same as the charge on an electron as well, but we'd sub it in as negative if it was an electron. So positive, that value, we have this negative here. Epsilon is given 175 newtons per coulombs times delta D is 1.5 meters. Now, because if this is our origin and we're moving from 1.7 or 1.45 to a final position of 2.95, so we're actually moving upwards. That's the ball is lifted up analogy. Oh no, wait. From if the proton's initial position is 1.45 meters from the origin and a final position of, okay. So yeah, we are lifting it up, and this should be initial and final. Just trying to think if this should be negative here. So final minus initial, we get a positive number. Positive number here. And oh, I guess I've written here that this must be the origin because our origin and a final position. Yeah, so this is the origin. So we're actually moving closer towards the negative plate, which is why we get, so this is like the ball dropping on its naturally. We've got a negative 4.2 times 10 to the minus 17 joules. Okay. For part B, it asks, using the law of conservation of energy, calculate the speed of the proton at the final position. So you thought you were done with last unit, but almost everything in this course builds. So the law of conservation of energy, well, the total energy at this point compared to the total energy at this point, are equal. Total mechanical energy at this point equals total mechanical energy at that point. Then total energy is made up of all the forms of potential energy and kinetic energy on one side equals all the forms of kinetic and potential energy on the other. So at the beginning, we're holding A. It's got stored energy, but there's no, just moving this small change for a proton, which has such a small mass, the delta Eg is insignificant. So we would not include that here. You can check if you wanted to include it, you can check to see how insignificant it is, but because the mass of a proton is so small, the delta Eg is negligible here. So EEA, so we hold it there, we've got stored energy at the beginning, and then at the end, we've still got a bit of stored energy because it's 1.45 meters away, plus speed. So we get that our EE at A, oh no, sorry, EE at A compared to EE at B. If we move this over to the other side, it's final, final minus initial, or I guess initial minus final. So I guess if I move this over, it's EEA minus EEB, which is the opposite of what I want. So that's why I actually add a negative here. So or sorry, delta EE, that is our number that we've already calculated. And then EEK, or sorry, EKB is 1/2 mv squared. If we solve for our speed, we sub in our numbers or isolate the equation for speed. I really can't talk today, I'm losing my voice. So speed is equal to 2.2 times 10 to the 5 meters per second. Okay, so that's example 1. For example 2, we have an electron moving from rest in a uniform electric field whose magnitude is 175 newtons per coulomb. Calculate the change in electric potential energy if the electron's initial position is, let me just double check the package here, but this is the exact same question with an electron. Okay, so we are going to do the same problem now with an electron. So we do know the charge of an electron is the same, it's just the opposite size. And so our initial position, we're going to say that the positive plate is our origin. And we start from a little bit away from the positive plate, and then we move to a final position of much further than the positive plate. So that's opposite to what the electron wants to do. So this is like the ball being lifted up, and we're giving it stored energy because the electron actually wants to move to the positive side. Calculate the change in electric potential energy for an electron accelerated in an electric field of, with the starting position. Okay, so B is a little bit different. So let's write out, let's write out this problem. So we draw our diagram again. Now the electron is moving from 1.45 to 2.95. So we say that this is our reference point of our position. So electron, we're going to have to put in work to move this electron from here to here. EE equal, or delta EE equals negative QED. We're going to substitute in those givens. And once again, the Q is the delta D is positive because, like I was trying to say in this example, we're moving from A to B. And this is our reference here. So from A to B for the proton is actually what it wants to do. So this is like a ball in free fall, which is why you get a negative delta EE. So it would be positive work done by the field. So I just wanted to clarify that. So now we have an electron doing the same thing, but this is the opposite of what the electron wants to do. So we've got stored energy gained. So it's the same value as the previous example, just not negative. And now to calculate, it's a different initial and final position. And because, oh, did you notice that because it's an electron, we subbed in a negative 1.6 times 10 to the minus 19 coulombs. So the reason why this is now positive instead of negative is because this was positive and this was negative and this was negative. So they cancel each other out. Yeah, so now we were going from, for part B, we have with the starting position of 1.45 to a final position of 4.55. So this would be a positive answer as well. So this should be positive. But anyways, this is a positive displacement that's different than the, oh, sorry, I need to read my own question. Calculate the change in electric potential energy for an electron accelerated in an electric field of negative 175. So actually now we flipped these for part B. So this is a good diagram for part A, but for part B, we flipped these, and epsilon is now pointing upwards and the electron is moving downwards. So here we go. Here's the diagram. So now we've got that. So that negative 175 says negative goes here, positive goes here. We're still moving from this spot, or like moving downwards on the page. So displacement is positive, epsilon is negative, Q is negative. So 3 negatives make a negative. So the electron is actually coming closer to what it wants to do. And so it's losing potential, it's losing stored energy. So this is like the ball in free fall. The electric potential energy decreases by 8.7 times 10 to the minus 17 joules. Oh yes, it's you should always interpret a negative before you write it in your therefore statement. So interpret the negative, whether it's a direction thing for a vector quantity or whether it's a gain or a loss in the energy unit. Okay, so just to recap, our equation is delta EE equals negative QED. So quick fact, maybe if you've done proofs in math, maybe your teacher has shown you this, but a neat little thing that you write at the end of a proof is QED, and it's Latin for, so it's quod erat demonstratum, and it's like, there, it has been proven. So it's kind of like to signify that you got to the end of a proof. So you know, in mathematical proofs, you take an equation and you say left side equals this, right side equals this, and then you do some substitution or rearranging or some algebra to kind of like make the left side equal to the right side. So you write left side equals right side, quod erat demonstratum. So I just like saying QED in this equation because it reminds me of what you write at the end of a mathematical proof, which is like the point where you're like, hey, I like proofs. It was satisfying before you move on to the next one. And okay, so the next part of this lesson, instead of the change in electrical potential energy, now we're going to talk about electric potential, which is V, and electric potential difference, which is delta V. So these are the equations that we're going to briefly go over, and then we'll do some examples. I do recommend the crash course in physics video that I'm going to link to the end of this. And a common application in this chapter is capacitors, which are like, it's a device to store electrical energy. So that's one thing that's covered in here. Just to clarify, we don't need to do detailed calculations. So this covers a little bit more than we need to know, but it is still useful conceptually to see. So electric potential is the electric potential energy per unit positive charge for a given point in an electric field. 1 volt is, you can see, 1 joule per coulomb. And yeah, so the SI unit is volts. And it's also equal to 1 Newton meter per coulomb because of the equivalent of a joule. And then this is a measure of how much electrical potential energy is associated with a specific quantity of charge at a particular location. And this is a convenient measure because it's independent of the amount of charge at that location. So it depends only on the electric field strength at that location. So for example, if you had 1 coulomb of electrons at a location in the field, there would be a certain electric potential energy associated with that location. If you double the charge to 2 coulombs at the same location, you double the electric potential energy. And in both of these scenarios, you'll have the same potential because it's the ratio. So all that matters is the electric field strength at that location. Potential so it's also known as, like for short, potential. Potential is scalar. Potential is independent of the amount of charge at the location. Depends only on the electric field strength. The volt is named after Alessandro Volta. So we've got electric potential difference, and it's the amount of work required per unit charge to move a positive charge from one point to another in the presence of an electric field. So another quantity we'd want to know is, again, when we're moving a charge, and it's the change in energy, the stored energy, compared to its charge size. And it's also scalar, and its unit is also volt. So for a uniform field, this equation can be combined with this equation to get a new equation. So delta V equals negative epsilon delta D. So this is only for a uniform field. And then in a non-uniform field, we can do rearrangement to, so in a non-uniform field, what's meant is that the magnitude of the electric field varies with the electric potential difference and the change in position in the field. So, so we can calculate that. So if epsilon is changing, we could calculate it if we know the delta V and the delta D. So we have some examples. Non-uniform means that the field strength changes as location moves away from the source of the field, such as when delta D changes. The field strength varies with the electric potential difference, and electric field points from regions of high potential to regions of low potential. To determine the direction of epsilon, you need to determine if delta V is negative or positive. And again, if you're a little confused as to how the electric field units could be newtons per coulomb or volts per meter, it might be good to check out this video, the one that I mentioned, the Crash Course in Physics video on this topic, because it explains it fairly well. Okay, so let's go to example 1. So we have an electron in an old computer monitor that leaves the negative plate and accelerates towards the positive plate. The electric potential difference between the plates is 1.8 times 10 to the 4 volts. Use the law of conservation of energy and the definition of electric potential difference to calculate the speed of the electron as it reaches the positive plate. Assume the electron is initially at rest. The mass of an electron is given. So let's draw a diagram first. So let's draw a diagram first. So we've got an electron here, and it's between 2 plates. And it starts out near the negative plate, and it's going to go towards the positive plate. It does that naturally because it's a negative charge and it wants to go to positive. So we know that there's going to be a loss in stored energy. And what's that stored energy going to turn into? It's going to turn into kinetic. So we've got total energy at point A when it's at the negative plate is equal to the total mechanical energy at point B. So ETA equals ETB. And what form of energy is at A? Well, it's assumed that it starts from rest. So we cancel EK. We cancel EG on both sides because the mass of this is it's insignificant. Actually, sorry, it's not because of that. It's because, Well, I guess the way we've drawn it, it's going horizontally, but that's not necessarily true. So if it's set up horizontally, then it's just the same value on both sides. There's no change in height. Or if it was set up vertically, the mass is so small. So when you're talking about a proton or electron, you can just by default, cancel out EG. So we've got EEA. So the stored energy at this point is going to turn into all turn into EK, kinetic energy at B. And through our equation, delta V equals delta EE over Q, we can isolate for delta EE. So I know you might say, oh, well, we have another equation for delta EE. Why don't we use that one? But we're given the potential difference, electrical potential difference. So since that's a given, we want to use this. We're not given epsilon, so we're not going to use QED. So a voltage times charge. We have both of those things. And then on the other side, the EK is equal to 1/2 mv squared. So you've got VQ equals 1/2 mv squared. This might be a little confusing with my messy writing. This V is small v, that's speed that goes into the EK equation. And this is big V, like delta V for potential difference. So we've got 2 delta V Q over M, and we substitute in the givens. Again, we need to look up that the charge on an electron is 1.6 times 10 to the minus 19 coulombs. And so for speed with 2 sig figs, we get 8.0 times 10 to the 7 meters per second. Calculate the magnitude of the electric field if the plate separation is 16 centimeters. Okay, we have an equation for the magnitude of the electric field. So we have an equation for the electric field if we have the potential difference divided by the displacement. So we sub those in and we get negative 1.1 times 10 to the 5 volts. So this is the equation that you would use if it was non-uniform. So whether it's non-uniform or not, we can use that equation. Okay, one last example. These are pretty challenging problems. So if I'm going through them too quickly, please pause. There's also 2 to 3 sample tutorial problems on page 352 and 353 that I do recommend going through, especially if you're finding this is a little bit fast. Okay, so we've got an electron with a horizontal speed passing through 2 horizontal parallel plates. As shown in the diagram, the magnitude of the electric field between the plates is 150 newtons per coulomb. The plates are 12.5 centimeters long. Calculate the vertical component of the electron's final velocity. So the electron has a horizontal velocity. The horizontal component of the velocity at all points will not be affected by passing through the plates, but the vertical component will. Because this is an electron, it's going to want to make its way over this way. So it's going to want to make its way closer and closer to the positive side, but it also has given this boost in the horizontal. And according to Newton's Newton's first law, objects in motion horizontally will continue in motion unless there's a force. So unless there was significant air resistance or friction horizontally, vertically, it's just going to get, its vertical component is going to accelerate towards the positive side. So does this kind of seem familiar? So if you flip it upside down, and that was the Earth's surface, it's kind of like a projectile. It's like a horizontal launch projectile problem where you have horizontally, it's uniform motion, and vertically you're accelerating towards the ground. So here, horizontally, we've got uniform motion, and vertically, we're accelerating up towards the positive plate because we are an electron, and this is the direction that a positive wants to go. So an electron wants to go the other way. So calculate the vertical component. So that's the component that has the acceleration. So if we want to know a velocity vertically, we're going to need to know acceleration. If we need to use acceleration, we'll need to find force first. So first of all, let's find what is the electric force acting on the electron being within this field. And this is the same force no matter where it is in the plate, as long as it's within the plate, because it's a uniform epsilon. So Q epsilon tells us the force, the electric force. And then, well, the electric force is making up the only force. So it's net force equals Fe. And we know net force is Ma. So we've got Ma equals Fe. So we can rearrange to solve for A equals Fe over M. And we get our acceleration, 2.63 times 10 to the 13 meters per second squared. And that's upwards towards the positive plate. Okay, so now we have our acceleration up. So we'll say up is positive. So we have our upwards acceleration. We're gonna start initially from 0 because initially when it enters the plates, the velocity is all horizontal. So this is kind of like the horizontal launch problem. So how tall is this velocity vector? It's 0 units tall. Okay, time. We don't have time, so how can we find time? So horizontally, we're told that the plates are 12.5 centimeters long, and we're looking for the velocity. It passes through, so it passes through to the other side. So it goes from here to there, and then as soon as it's out, there's no more acceleration towards a positive plate. So really we care about from here to here, that's our displacement in the x, and we've got our velocity in the x. So we do Vx equals dx over t, because horizontally it's uniform motion. We can find time, and time is connecting the vertical and horizontal section sides. Now we've got a VIY, or AY, VIY, and T. We look to our kinematic equations, and the one that will connect those three things together with VFY is the first one. So we substitute those in, and we get VFY equals 2.1 times 10 to the 6 meters per second. Part B is calculate the final velocity of the electron. So the final vertical velocity is it's going up at that speed, but overall velocity is at an angle like this. So we need to consider the horizontal component of this and the vertical component of this final velocity vector. And luckily we've already got our VFX because it didn't change. It was the one that was given in the question. Our VFY is what we just calculated. We're going to use the unrounded number. So make sure you're not using 2.1. And then we get, so Pythagorean theorem to calculate the hypotenuse of this triangle, which is the components triangle of the vector, of the final velocity vector. And then we can solve for theta, which is this angle here, using tan inverse, and we get 52 degrees. The final velocity is 2.6 times 10 to the 6 meters per second, which is 52 degrees up from the right, based on the diagram. So that word right is only relevant if you have or created a diagram. Okay, so it's time for you to do some practice questions. Please make sure to fill out the exit ticket for this video to kind of, the exit ticket is not meant to be like tricky or challenging, although I'm kind of having fun with them. The exit ticket is literally just meant to be like a check-in. Like you see that the video is posted, you watch the video, and then you know, you're trying your best on the practice questions, and I know there's a lot of the workload in a lot of courses. So just try your best. Submit your practice question answers to Google Classroom as soon as you have them, and then I can try and give you feedback. These are challenging, like this section and the next one, they're challenging questions, so please email me if you have any questions, and be safe. Have a great day.